What if I told you that right now, as you sit there watching this video, there exists a place in our universe so impossibly empty, so unfathomably vast, that it challenges everything we thought we understood about reality itself? A place where you could travel at the speed of light, covering 300,000 kilometers every single second, and still need over 300 million years just to cross from one side to the other. A place where 10,000 galaxies should exist, each containing hundreds of billions of stars, trillions of planets, countless possibilities for life, and yet when scientists pointed their telescopes in that direction, they found almost nothing, just darkness, just emptiness, just a void so large that it shouldn't exist. I want you to pause for a moment and think about the darkest place you have ever been. Maybe a cave with the lights turned off. Maybe a remote location far from city lights where you looked up and saw the Milky Way stretching across the sky. Now, I want you to imagine something far more profound. Imagine being in a place so dark, so isolated, so cut off from everything else in the universe, that if you were born on a planet there, you might live your entire existence. Your entire civilization might rise and fall without ever knowing that other galaxies existed at all. Because from the center of this void, looking out in any direction, you would see almost nothing. No spiral galaxies spinning majestically in the distance. No galactic clusters blazing with the light of trillions of stars. Just an endless, an incomprehensible expanse of darkness stretching in every direction for hundreds of millions of light years. This is the Boötes Void. This is the largest known structure of emptiness in our observable universe. And this is the mystery that has kept astronomers awake at night for over 4 decades, because according to everything we understand about how our universe formed and evolved, this void simply should not be there. It is too big, it is too empty, it is too perfect in its nothingness. And yet, there it is, a cosmic anomaly lurking approximately 700 million light-years away from Earth, silently challenging us to explain its impossible existence. Before we dive deep into this cosmic mystery, let me give you some numbers that will make your head spin. The Boötes Void stretches approximately 330 million light-years across. Some measurements suggest it might be even larger, perhaps up to 500 million light-years in diameter. To put that in perspective, our entire Milky Way galaxy, the cosmic island that contains our solar system, our planet, everything we have ever known or loved, is roughly 100,000 light-years across. That means you could line up over 3,000 Milky Way galaxies across the diameter of the Boötes Void and still have room to spare. Our nearest major galactic neighbor, the Andromeda Galaxy, is approximately 2.5 million light-years away, and that distance seems almost incomprehensible to us. We measure it in millions of years at the speed of light. Yet the Boötes Void is over 100 times larger than the gulf that separates us from Andromeda. Let that sink in for a moment. Now here is where things get truly strange. Based on the average density of matter in our universe, astronomers calculated that a region of space this size should contain approximately 10,000 galaxies. 10,000 entire galaxies, each one a vast collection of stars, gas, dust, and dark matter, each one potentially harboring billions of planets, each one representing almost infinite possibilities. And yet when researchers carefully surveyed the Boötes Void, counting every galaxy they could find within its boundaries, they discovered something shocking. There were only about 60 galaxies inside, 60 where there should be 10,000. That is a deficit of over 99%. Imagine expecting a city of 10,000 people and finding only 60 inhabitants scattered across an impossibly vast landscape, each one separated from their nearest neighbor by an average of 10 million light-years. That is the Boötes Void. If you find this journey into cosmic emptiness fascinating, if you're the kind of person who lies awake at night wondering about the universe's deepest mysteries, then I think you and I are going to get along very well. We're about to go on a voyage that will take us from the fundamental structure of reality to questions about the fate of our entire cosmos. We will explore how this void was discovered, why it challenges our best scientific theories, and what it might tell us about the true nature of existence itself. So if you have not already, take a moment to subscribe to this channel and hit that notification bell, because I promise you, by the end of this video, you will never look at the night sky the same way again. And drop a comment below telling me what you think might be hiding in the largest void in the known universe. Is it evidence of something beyond our understanding? A glitch in the fabric of reality? Or perhaps something even more extraordinary that we have not yet imagined? Let us find out together. To truly understand why the Boötes Void is so extraordinary, we first need to understand how our universe is structured on the larger scales. And I have to tell you, when scientists first began mapping the cosmos in detail, what they discovered was nothing short of breathtaking. Our universe is not randomly distributed. Matter is not scattered evenly throughout space like dust sprinkled uniformly across a table. Instead, the cosmos has an intricate, beautiful, almost organic structure that scientists call the cosmic web. Imagine you're looking at a vast three-dimensional network of interconnected filaments, like a cosmic spider web stretching across billions of light years. Along these filaments, galaxies cluster together in long chains and sheets, connected to massive nodes where thousands of galaxies congregate in enormous clusters. These clusters are connected to even larger structures called superclusters, vast collections of galaxy clusters that can span hundreds of millions of light years. And between all of these filaments and clusters and walls of galaxies, there are regions of relative emptiness. These are the cosmic voids. But here is the crucial thing to understand. Cosmic voids are a normal and expected part of the universe's structure. They form naturally as gravity pulls matter together into the filaments and clusters, leaving behind regions that become progressively emptier over time. Think of it like this. Imagine you have a bathtub full of water with small floating particles distributed throughout. Now imagine you start creating areas of attraction that pull those particles together into clumps and strings. As the particles accumulate in certain regions, other regions become relatively empty. That is essentially what happened in our universe over billions of years, with gravity acting as that attractive force and galaxies being those floating particles. Scientists have discovered many cosmic voids throughout the observable universe. The local void, which our own Milky Way sits near the edge of, stretches about 150 million light-years across. The Sculptor Void is another notable example, spanning around 400 million light-years. These voids are large, certainly, but they fit within the predictions of our cosmological models. They have the expected density of matter based on their size. They formed in ways that our physics can explain. But the Boötes Void is different. The Boötes Void breaks the rules. Let me take you back to 1981, because that is when this mystery truly began. 4 astronomers named Robert Kirshner, Augustus Umler Jr., Paul Schechter, and Stephen Schechtman were conducting a systematic survey of galaxies in different regions of the sky. They were using a technique called redshift measurement to determine the distances to various galaxies, essentially creating a three-dimensional map of the cosmos around us. It was painstaking work, requiring careful observation of hundreds of galaxies, measuring how much the light from each galaxy had been stretched by the expansion of the universe. The more redshifted the light, the farther away and faster receding the galaxy. As they compiled their data, plotting galaxy after galaxy onto their cosmic map, they began to notice something strange in the direction of the constellation Boötes. There was a gap in their data. A big gap. At first, they probably assumed it was some kind of observational error or a region they simply had not surveyed thoroughly enough. But as they continued their work, the gap remained, and it kept growing. Where they expected to find hundreds of galaxies at a certain distance range in that part of the sky, they found almost nothing. The emptiness was staggering in its extent. I want you to imagine what that must have felt like for those scientists. You're methodically mapping the universe, expecting to see the same general distribution of matter that you see in every other direction, and suddenly you encounter a void so vast and so empty that your first instinct is to check your equipment. Surely something must be wrong with the telescope. Surely there must be some absorbing material blocking our view. Surely the universe cannot be this empty in any one direction. But no matter how many times they checked, the void remained. It was real. When Kirshner and his colleagues published their discovery, they described finding a region approximately 250 million light-years across containing essentially no galaxies. Later observations would reveal that the void was even larger than their initial estimates, stretching to 330 million light-years or more. The scientific community was intrigued but also skeptical. How could such an enormous empty region exist? What cosmic process could have evacuated such a vast volume of space? To understand why the Boötes Void posed such a problem, you need to understand the standard model of cosmology, which describes how our universe evolved from the Big Bang to its present state. According to this model, called lambda CDM, the universe began in an extremely hot, dense state approximately 13.8 billion years ago. In those earliest moments, dust matter was distributed almost perfectly uniformly throughout space, but not quite perfectly. There were tiny variations in density, quantum fluctuations from the very first moments of existence, regions that were slightly denser or slightly less dense than average. Over billions of years, gravity went to work on these tiny variations. Regions that were slightly denser attracted more matter, becoming even denser over time. Regions that were slightly less dense lost matter to their denser neighbors, becoming progressively emptier. This is how the cosmic web formed, with matter accumulating along filaments and in clusters, while voids expanded in between. It is a beautiful process of cosmic evolution, and our computer simulations can reproduce the general structure of the universe remarkably well using just these basic principles. But here is the problem with the Boötes Void. According to our models, 13.8 billion years is simply not enough time for a void this large, and this empty, to form through normal processes. The universe is too young. For a region to become as devoid of matter as the Boötes Void appears to be, it would need to have started with an initial density far below average, and then evolved for much longer than the age of our universe allows. The numbers simply do not work. This is what scientists call a 6 sigma anomaly, meaning the probability of such a void existing by chance, according to our standard models, is extraordinarily low. It is the kind of statistical improbability that makes researchers either question their data or question their theories. Let me paint a picture for you of what it would be like to exist within the Boötes Void. Imagine a civilization arising on a planet orbiting a lonely star in one of those 60 isolated galaxies, scattered throughout this cosmic wilderness. This hypothetical species develops intelligence, creates technology, begins studying the heavens above them. What would they see when they looked up at their night sky? From the center of the Boötes Void, the nearest major galaxy cluster is hundreds of millions of light-years away. Even with advanced telescopes, detecting such distant objects would be extraordinarily challenging. It is entirely possible that such a civilization would develop their entire understanding of the cosmos believing they were alone, that their galaxy was the only island of matter floating in an infinite sea of darkness. They would have no evidence of the vast cosmic web that we can see from our privileged position. No knowledge of the billions of galaxies that fill our telescopic views. They would look out and see only the void. Now consider how different their philosophical and scientific development might be. We humans have always wondered about our place in the cosmos, but our night sky is full of clues about the larger universe. Ancient peoples could see the band of the Milky Way stretching overhead. As our technology improved, we discovered other galaxies, then clusters of galaxies, then the large-scale structure of the cosmic web. Each discovery pushed us to see ourselves as part of something larger. But a void civilization would have none of these contextual clues. Their night sky would offer only darkness and mystery. Would they even think to wonder about other galaxies if they had no evidence such things existed? There is a remarkable and somewhat chilling statistic related to this thought experiment. If Earth were located at the center of the Boötes Void instead of in our relatively dense neighborhood of the local group, we would not have discovered the existence of external galaxies until the 1960s. That is because the Andromeda Galaxy, which is visible to the naked eye from our actual location, would be so impossibly distant from the void center that we would have needed sophisticated 20th century telescopes to detect it. The entire history of human astronomy, from ancient stargazers to Edwin Hubble's discovery that the universe extends beyond our galaxy, would have been compressed into just a few decades of revelation rather than millennia of gradual understanding. Speaking of those few galaxies that do inhabit the Boötes Void, they represent a fascinating subject of study in their own right. These cosmic hermits live in extreme isolation, typically separated from their nearest neighbor by about 10 million light-years. To put that in perspective, our Milky Way's nearest major galactic neighbor, the Andromeda Galaxy, is about 2.5 million light-years away. So the void galaxies are separated by roughly 4 times the distance between us and Andromeda, and they have far fewer neighbors in total. This isolation has profound effects on how these galaxies evolve. In denser regions of the universe, galaxies frequently interact with each other. They pass close enough to gravitationally perturb each other, sometimes triggering bursts of star formation, sometimes stripping gas from one another, sometimes merging entirely into larger hybrid galaxies. Our own Milky Way bears the scars of ancient collisions and will eventually merge with Andromeda in about 4.5 billion years. These interactions drive much of galactic evolution, stirring up gas, igniting stellar nurseries, reshaping galactic structures. But in the void, such interactions are extraordinarily rare. The galaxies there evolve in near-perfect isolation, following their own internal processes without external perturbation. They are, in a sense, pristine laboratories for understanding galactic evolution in its purest form. Scientists have found that void galaxies tend to be bluer in color than their counterparts in denser regions, indicating ongoing star formation that has not been disrupted or exhausted by interactions. They tend to be smaller on average, having not grown through mergers. They often have more irregular shapes, not having been tidally regularized by passing neighbors. But here is something even more peculiar about the Boötes Void. When astronomers mapped the distribution of those 60-odd galaxies within it, they discovered something unexpected. The galaxies are not randomly scattered throughout the void. Instead, they appear to be arranged along a thin, tube-like structure running through the void like a lonely filament of the cosmic web that somehow persists within this vast emptiness. This tubular galaxy distribution stretches for hundreds of millions of light-years, and no one quite understands why it exists or how it survived. One possibility is that this tube represents the remnant of a cosmic web filament that once connected denser regions on either side of what is now the void. As the void expanded and matter flowed outward toward the surrounding walls, this filament managed to persist, perhaps feeding on dark matter that flows along its length, or protected by some quirk of gravitational dynamics. Another possibility is that the tube represents the last traces of matter that are still in the process of draining out of the void, frozen in place as we happen to observe them during this particular cosmic epoch. Either way, and this unexpected structure adds another layer of mystery to an already puzzling cosmic phenomenon. Now let us grapple with perhaps the most vexing question of all. How did the Boötes Void form in the first place? As I mentioned earlier, our standard cosmological models struggle to explain a void of this size and emptiness given the age of the universe. But scientists are nothing if not creative in developing hypotheses, and several competing theories have emerged over the decades since the void's discovery. The first and most conservative explanation is that the Boötes Void formed from an unusually large underdensity in the primordial universe. Remember those tiny density fluctuations I mentioned, the quantum perturbations from the earliest moments after the Big Bang? Most of these fluctuations were small, leading to the gradual formation of the cosmic web we observe today. But perhaps, just perhaps, there was an unusually large negative fluctuation in the region that would become the Boötes Void. This region started out significantly less dense than its surroundings, giving it a head start in becoming empty. Over billions of years, matter continued to flow out of this region while it expanded, eventually creating the supervoid we observe today. This explanation has the advantage of working within our existing physical framework. It does not require any new physics or exotic phenomena. It simply proposes that the Boötes Void represents an extreme but not impossible outcome of the same processes that shape the rest of the universe. The problem is probability. Such an extreme primordial underdensity is statistically very unlikely. Not impossible, but unlikely enough that its existence alone suggests there might be more to the story. The second major theory proposes that the Boötes Void is not a single primordial feature, but rather the result of multiple smaller voids merging together over cosmic time. Imagine several ordinary-sized voids, each one forming normally according to our standard models, but happening to be located near each other. As each void expands, it eventually begins to overlap with its neighbors. The thin walls of matter separating them collapse or drain away, and the voids merge into a single larger structure. Repeat this process several times, and you could potentially create a supervoid much larger than any single void could grow to on its own. This bubble merger hypothesis has some attractive features. It explains how a structure larger than our models predict could form within the age of the universe. It is consistent with observations that show the Boötes Void has a somewhat irregular shape rather than being a perfect sphere, and computer simulations have shown that such void mergers do occur, though creating something as large and empty as the Boötes Void would still require some fortunate circumstances. The question is whether the required merger history is plausible, given what we know about void distribution in that region of space. The third theory gets a bit more speculative but is no less fascinating. It proposes that the Boötes Void might contain an unusual concentration of dark energy, the mysterious force driving the accelerating expansion of our universe. In the Standard Model, dark energy is assumed to be uniformly distributed throughout space, a constant value at every point called the cosmological constant. But what if dark energy is not perfectly uniform? What if there are regions where it is slightly more concentrated than others? If dark energy were more concentrated within the Boötes Void, it would cause space in that region to expand faster than surrounding areas. This accelerated local expansion would push matter outward more rapidly, creating a larger and emptier void than normal processes would allow. It would also cause the void to grow faster over time, potentially explaining its current enormous size. This hypothesis has interesting implications for our understanding of dark energy, and could be tested by precise measurements of the expansion rate within and around the void. So far, such measurements remain at the edge of our technological capabilities, but future observations might provide definitive evidence for or against this idea. Now, we come to some of the more exotic and controversial explanations, theories that venture beyond mainstream cosmology into the realm of speculative physics. I present these not as established science, but as fascinating possibilities that at least some researchers have taken seriously enough to investigate. One such theory invokes cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during phase transitions in the early universe. Think of them as cracks or wrinkles in the fabric of reality itself, incredibly thin but potentially stretching across vast cosmic distances. If a cosmic string existed in the region that would become the Boötes Void, its immense gravitational influence could have pushed matter away from it, seeding the formation of an unusually large void. Some physicists have proposed that large cosmic voids might serve as evidence for the existence of such exotic structures. Even more speculatively, some researchers have suggested that enormous cosmic voids like the Boötes Void might be evidence for the multiverse. According to certain inflationary cosmology theories, our universe might be just one bubble in an infinite foam of universes, each with its own properties and physical laws. If our universe collided with a neighboring bubble universe in its early history, the collision could leave behind a distinctive signature, potentially including an anomalously large and empty region, where the collision disrupted normal matter distribution. This is highly speculative, to be clear, but it is the kind of speculation that arises when confronted with phenomena that seem to challenge our standard explanations. And then there is the hypothesis that I almost hesitate to mention, because it sounds so much like science fiction, but which has been discussed in certain corners of theoretical physics. What if the Boötes Void is artificial? What if some incredibly advanced civilization, operating on scales we can barely imagine, deliberately cleared out this region of space for purposes we cannot fathom? A Kardashev Type 4 or 5 civilization, one that harnesses the energy of entire clusters of galaxies, or the universe itself, might have the capability to move matter across hundreds of millions of light years. Perhaps the void is a construction project, a cleared zone for some cosmic infrastructure we cannot detect. Or perhaps it is a quarantine region, a buffer zone between cosmic domains. I should emphasize that there is absolutely no evidence for this idea, and most scientists would dismiss it as unfounded speculation. But it illustrates how the Boötes Void's sheer inexplicability invites even the wildest hypotheses. What does mainstream science currently believe? The consensus view, such as it exists, leans toward a combination of the primordial underdensity and void merger hypotheses. The Boötes Void probably did start out as an unusually underdense region in the early universe, giving it an initial advantage in becoming empty. Over billions of years, it may have absorbed several smaller neighboring voids, growing larger than any single void could have become alone. This combination of factors could potentially explain the void's size and emptiness without requiring new physics, though significant uncertainties remain. But even this consensus view comes with caveats and open questions. We still do not fully understand why the primordial density fluctuations in this region would have been so extreme. We still cannot fully reconcile the void's properties with our best computer simulations of cosmic structure formation. And we still have much to learn about the void's internal structure, its exact boundaries, and its relationship to the surrounding cosmic web. The Boötes Void remains in many ways an unsolved mystery. Let me now expand our perspective and consider what the Boötes Void and other cosmic voids tell us about the ultimate fate of our universe. This is where our journey into emptiness becomes truly contemplative, touching on questions about the future of everything that exists. Our universe is expanding. This is one of the foundational discoveries of modern cosmology, first observed by Edwin Hubble in the 1920s and confirmed countless times since. Galaxies are moving apart from each other, and the space between them is growing. But here is the truly remarkable part. This expansion is accelerating. In 1998, two independent teams of astronomers made the shocking discovery that the universe's expansion is not slowing down under gravity's influence, as everyone expected, but actually speeding up. Something is pushing the cosmos apart faster and faster over time. We call this something dark energy, and despite decades of research, we still do not know what it is. It makes up approximately 68% of the total energy content of the universe, yet it remains one of the deepest mysteries in physics. What we do know is that dark energy's influence grows stronger as the universe expands and matter becomes more diffuse. And this has profound implications for cosmic voids. As the universe continues to expand and dark energy's influence grows, the cosmic web is essentially being stretched apart. The filaments connecting galaxy clusters are being pulled thinner. The walls separating voids are becoming more tenuous, and the voids themselves are growing larger and emptier. In effect, the universe is slowly transitioning from a web-dominated structure to a void-dominated structure. The Boötes Void, in this sense, might be a preview of the universe's future state, a glimpse of the increasing emptiness that awaits all of cosmic structure. If we project this process forward, the far future of our universe looks increasingly lonely. Trillions of years from now, the cosmic web will have stretched to the breaking point. Galaxy clusters will become isolated islands separated by voids so vast that light from one cluster could never reach another, even given infinite time. The universe will fragment into countless causally disconnected regions, each one essentially a separate universe with no possibility of communication or interaction with any other. Within these isolated pockets, galaxies will continue to evolve, but without the possibility of new material arriving from outside their cluster. Star formation will eventually cease as gas is exhausted. Stars will burn out one by one. From the hottest blue giants to the longest-lived red dwarfs, the only light will come from the cooling embers of white dwarfs and the faint glow of brown dwarfs never massive enough to truly shine. Eventually, even these will fade. Black holes will be the last macroscopic objects, slowly evaporating over incomprehensible timescales through Hawking radiation. This is the heat death of the universe, the maximum entropy state where all energy has been evenly distributed and no further useful work can be done. It is, in essence, one vast cosmic void with nothing but the faintest trace of thermal radiation spreading ever thinner through ever-expanding space. If the Boötes Void seems lonely and empty to us now, imagine a universe where everywhere is the Boötes Void, where the darkness and silence that characterize this anomalous region have become the universal norm. I find this vision both terrifying and strangely beautiful. Terrifying because it speaks to the ultimate impermanence of everything we know and love, the eventual extinction of all complexity and structure. Beautiful because there is something profound about the universe's ultimate simplicity, its return to a state of perfect equilibrium after billions and trillions of years of cosmic drama, and the Boötes Void stands as a reminder of this distant fate, a preview screened in our cosmic present of the movie that will eventually play everywhere. But let me step back from this ultimate vision and return to something more immediate and perhaps more hopeful. What can we learn from studying the Boötes Void? What scientific advances might emerge from understanding this cosmic anomaly? First and most directly, the Boötes Void serves as a laboratory for understanding dark energy. Because voids are dominated by dark energy rather than matter, they provide our best opportunity to study dark energy's behavior at different scales and in different environments. If dark energy is truly a constant, as the simplest models predict, then it should behave the same inside the Boötes Void as everywhere else. But if dark energy varies in space or time, voids might be where we first detect such variations. The growth rate of voids, their shape evolution, and their impact on passing light rays all provide clues about dark energy's true nature. Second, the Boötes Void helps us test our theories of gravity at cosmic scales. General relativity. Einstein's theory of gravity has been confirmed to extraordinary precision in our solar system and in the strong gravitational fields near black holes and neutron stars. But on the scales of cosmic voids, where gravity is extremely weak and dark energy dominates, general relativity has been tested less thoroughly. Some modified gravity theories predict different void properties than general relativity does, so careful observations of large voids could help distinguish between competing gravitational theories. Third, cosmic voids provide a unique window into the cosmic microwave background radiation, the ancient light from the early universe that pervades all of space. When CMB photons travel through a void, they experience what is called the integrated Sachs-Wolf effect. As the photon enters the void, it gains energy by falling into the gravitational potential well, but as the void expands while the photon crosses it, the potential well becomes shallower, and the photon does not lose as much energy climbing out as it gained falling in. The result is a net blue shift of the photon, which translates to a slightly warmer temperature in the CMB at that location. This effect has actually been observed. There is a famous feature in the CMB called the cold spot, an unusually cold region in the direction of the constellation Eridanus that has puzzled cosmologists since its discovery in 2004. Some researchers propose that this cold spot might be caused by a supervoid along that line of sight, and subsequent observations did reveal an enormous void, dubbed the Eridanus supervoid, roughly in the right location. However, its detailed calculations suggest that the Eridanus supervoid alone cannot fully account for the cold spot's temperature deficit, leaving open the possibility that something else contributes to this anomaly. This brings us to one of the most fascinating and controversial proposals in modern cosmology, the idea that anomalies like the CMB cold spot and large cosmic voids might be evidence for the multiverse. Physicist Laura Massini-Houghton has championed the hypothesis that the cold spot and possibly other cosmic anomalies represent a bruise left by our universe's collision with a neighboring bubble universe in the moments after the Big Bang. According to this proposal, the collision would have imparted energy and matter in a distinctive pattern, potentially creating both a cold spot in the CMB and an unusually large void in the matter distribution. This is an extraordinary claim, and extraordinary claims require extraordinary evidence. Most cosmologists remain skeptical, pointing out that the observed anomalies can potentially be explained by more mundane processes within our standard cosmological model. Statistical flukes, imperfect data analysis, and incomplete theoretical understanding all remain possibilities. Yet the proposal has not been definitively ruled out, and it illustrates how the study of cosmic voids connects to some of the deepest questions in physics. Are we alone in the multiverse? Is our universe truly all there is, or just one bubble in an infinite foam? The answers might be written in the distribution of matter on the larger scales, in the patterns of emptiness that span hundreds of millions of light years. Let me now describe the observational techniques astronomers use to study the Boötes Void and similar structures, because the technical challenges are formidable. How do you study something that is, by definition, almost empty? How do you map the boundaries of nothing? The primary technique is galaxy redshift surveys, which systematically measure the positions and distances of enormous numbers of galaxies. By compiling catalogues of hundreds of thousands or millions of galaxies, each with its three-dimensional position determined, astronomers can construct maps of the cosmic web and identify the voids within it. The Sloan Digital Sky Survey, which began in 2000 and has imaged roughly 1/3 of the sky and measured redshifts for millions of galaxies, has been particularly valuable for void studies. More recent surveys like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory will provide even more detailed maps. Another approach is to study the effects of voids on light passing through them. As I mentioned, the integrated Sachs-Wolf effect imprints a signature on the CMB at the locations of large voids. By cross-correlating CMB temperature maps with galaxy surveys, astronomers can detect and characterize voids even when their individual galaxy content is too sparse to map directly. Gravitational lensing, the bending of light by massive structures, provides another probe. Voids produce a distinctive weak lensing signal, slightly demagnifying and distorting the images of background galaxies. Measuring this effect statistically across many voids helps constrain their mass distribution and density profiles. Radio observations offer yet another window into void structure. Neutral hydrogen gas, which fills much of the intergalactic medium, emits radio waves at a characteristic wavelength of 21 centimeters. By mapping this emission, astronomers can study the distribution of gas within and around voids, providing information complementary to optical galaxy surveys. The upcoming square-kilometre array, when completed, will revolutionize this field, mapping hydrogen across cosmic history with unprecedented sensitivity and resolution. The James Webb Space Telescope, which began science operations in 2022, brings another powerful tool to void studies. While JWST was designed primarily for studying the early universe and the formation of galaxies and stars, its extraordinary sensitivity allows it to detect extremely faint and distant galaxies that previous telescopes could not see. This means JWST can help determine whether some voids that appear empty actually contain populations of very faint dwarf galaxies that were below our detection threshold. If so, our estimates of void emptiness might need revision. If not, the voids really are as empty as they appear, deepening the mystery. Speaking of JWST and my knowledge of recent developments, I should note that my information about very recent discoveries is limited by when my knowledge was last updated. The study of cosmic voids is an active field, and new findings emerge regularly. I encourage you to seek out the latest research papers and news reports for the most current state of our understanding. What I can tell you is the fundamental principles and the broad outlines of the mystery, which remain compelling regardless of any recent incremental advances. For those of you watching this who are amateur astronomers or simply curious about the night sky, you might be wondering whether you can observe the Boötes Void yourself. The answer is yes and no. You can certainly point your telescope at the region of sky where the void is located, roughly centered at right ascension 14 hours, 50 minutes, and declination 46 degrees. The constellation Boötes is visible from much of the northern hemisphere during spring and summer evenings, marked by the bright star Arcturus. But what you will see, or rather not see, might be underwhelming. The Boötes Void is 700 million light-years away. At that distance, even large galaxies appear as tiny smudges requiring substantial telescopes to detect. The galaxies within the void are scattered sparsely across a region much larger than your telescope's field of view. From a practical standpoint, you will not see anything dramatically different looking at the void compared to any other deep sky region. The emptiness is apparent only when you compile systematic surveys of galaxy positions and notice the gap in three-dimensional space. What you can appreciate, however, is the direction. When you look toward Boötes, you are looking toward that unimaginable emptiness, that vast expanse of darkness where light takes hundreds of millions of years to cross, and where civilizations, if they exist at all, would know a loneliness we can barely conceive. There is something profound about directing your gaze toward the largest void we know of, even if your eyes cannot see its emptiness directly. You are connecting, in your imagination, with one of the universe's strangest and most mysterious structures. Let me now shift to a more philosophical register, because I think the Boötes Void invites contemplation beyond the purely scientific. What does it mean that such vast emptiness exists? What does it tell us about our place in the cosmos? Humans have always had an ambivalent relationship with nothingness. Across cultures and throughout history, voids and emptiness have been objects of both fear and fascination. In many religious and philosophical traditions, the void represents chaos, the absence of divine order, as something to be filled or overcome. In others, particularly in certain Eastern philosophies, emptiness is seen more positively as a fundamental aspect of reality, a pregnant nothingness from which all things arise. The Boötes Void can be approached through either of these lenses. On one hand, it represents an almost unfathomable desolation, a cosmic desert that makes the loneliest places on Earth seem bustling by comparison. If you find meaning in the richness and complexity of the universe, in the countless worlds and possible forms of life that exist within it, then the Boötes Void might seem like a tragedy, a vast region from which nearly all that richness has been excluded. On the other hand, there is something sublime about the void's sheer scale. It reminds us that the universe operates on dimensions that transcend human concerns entirely. Our worries, our ambitions, our entire history as a species, all of it fits within a fraction of the void's immensity. This can be humbling in the best sense. a reminder that our perspective is limited and that reality extends far beyond what we can directly experience or easily imagine. The void also raises questions about life and its distribution in the cosmos. If the universe contains regions as empty as the Boötes Void, then life is clearly not everywhere. Complexity and habitability cluster in certain regions and are absent from others. This might seem obvious, but the sheer contrast between our local neighborhood, which teems with galaxies and stars and planets, and the void's near-perfect emptiness drives the point home viscerally. We live in a cosmically privileged location, a place where there is enough matter and enough neighboring stars and galaxies to make our existence possible. The void dwellers, if they exist at all, inhabit a fundamentally different kind of cosmos. Some thinkers have drawn connections between cosmic voids and the Fermi paradox, the puzzling absence of evidence for extraterrestrial civilizations despite the vastness of the universe. One possible resolution to the paradox is that intelligent life is extremely rare, scattered so sparsely across the cosmos that civilizations almost never encounter each other. If true, most intelligent beings would find themselves in situations analogous to those hypothetical void civilizations, isolated and alone in their cosmic neighborhood, potentially never discovering that others exist elsewhere. The Boötes Void makes this possibility visceral. It shows us what cosmic loneliness looks like on the larger scales. But let me offer a more hopeful perspective as well. The very fact that we have discovered the Boötes Void, that we have mapped it and measured it and theorized about its origin, speaks to something remarkable about human beings. We are creatures of a small rocky world orbiting an ordinary star in an ordinary galaxy, yet we have managed to detect and characterize a structure hundreds of millions of light-years across. Our minds, evolved to navigate African savannas and social hierarchies, have somehow gained the capacity to comprehend cosmic architecture. The void humbles us certainly, but our ability to know it, to reason about it, to feel wonder at it, represents a kind of cosmic triumph. And the mystery remains, which is perhaps the best part of all. We do not fully understand the Boötes Void. Its existence still challenges our theories and invites further investigation. In an age when it sometimes seems like all the big discoveries have been made and all the fundamental questions answered, the void reminds us that the universe still holds secrets. There are still things that surprise us, still phenomena that do not quite fit our models, still mysteries worth pursuing. For scientists and for anyone who finds meaning in the pursuit of understanding, this is a gift. I want to spend some time now on a question that particularly fascinates me. What would it be like for a civilization to develop within the Boötes Void? And how might their understanding of the universe differ from ours? Consider first the night sky. For us, the night sky is rich with celestial objects. From any dark location on Earth, you can see thousands of stars with the naked eye, all of them members of our Milky Way galaxy. The band of the Milky Way itself stretches overhead, revealing the disk of our galactic home. With even modest binoculars, you can spot the Andromeda galaxy, a fuzzy patch of light that is actually an entire galaxy containing 1 trillion stars located 2.5 million light-years away. Larger telescopes reveal countless more galaxies, a universe teeming with cosmic islands in every direction. Now imagine the night sky from a planet near the center of the Boötes Void. First, you would still see the stars of your own galaxy. Assuming your planet is in one of those 60 isolated void galaxies, your local night sky might not look dramatically different from ours in that respect. But once you looked beyond your galaxy, once you developed the technology to see fainter and more distant objects, you would encounter a profound emptiness. The nearest other galaxy might be 10 million light-years away, far too faint to see with anything but the most powerful telescopes. The cosmic web, the vast network of filaments and clusters that surrounds the void, would be hundreds of millions of light-years distant, utterly invisible to any reasonable observation. Think about how this would affect the development of astronomy as a science. For us, the discovery that the Andromeda Nebula was actually a separate galaxy, comparable in size to our own Milky Way, was a pivotal moment in the history of science. It happened in the 1920s when Edwin Hubble measured the distance to Andromeda using Cepheid variable stars. This discovery transformed our understanding of the cosmos, revealing that the universe extended far beyond our single galaxy to encompass billions of similar structures. For a void civilization, this discovery might never happen, or it might be delayed by centuries or millennia. The faint smudges that our telescopes easily resolve into galaxies would, for them, be dim and distant objects requiring technology far beyond what Hubble had available. Their astronomers might speculate about whether those faint patches of light were external galaxies, but they would have extreme difficulty proving it. Their cosmology might develop very differently, perhaps focusing more on their own galaxy's structure and evolution, perhaps developing sophisticated theories about the nature of the dim, barely detectable objects at the edge of their observational capabilities. And what about their philosophy, their religion, their sense of place in the universe? Human cultures have always looked to the sky for meaning. We have seen gods and myths written in the patterns of stars. We have felt both insignificance and connection when contemplating the vastness above us. But the vastness we contemplate is full, rich with stars and galaxies and the promise of other worlds. A void civilization would contemplate a vastness that is empty, a darkness extending without end in every direction. How might this shape their existential reflections, their creation myths, their sense of whether they are alone? It is possible that such a civilization would have a deeper appreciation for the rarity and preciousness of matter and complexity. Surrounded by such overwhelming emptiness, the mere existence of their star, their planet themselves would seem all the more miraculous. They might develop a particularly intense sense of gratitude for existence, knowing that existence itself is a statistical anomaly in their vast barren cosmos. Or they might feel a profound loneliness, a cosmic isolation that permeates their culture and philosophy. We can only speculate, but the speculation itself illuminates how our own cosmic context shapes our thoughts and feelings about existence. There is another angle to consider. If intelligent civilizations are spread throughout the universe, even sparsely, then the Boötes Void represents a vast region where such civilizations are unlikely to encounter each other. For a void civilization, the dream of contact with other intelligent beings might seem even more remote than it does for us. They would know, if they had developed sophisticated astronomy, that other galaxies exist at unimaginable distances, and they might infer that intelligent life could have arisen there. But the prospect of ever communicating with such distant civilizations, let alone meeting them, would be essentially zero. Their isolation would be not just current but eternal, a fundamental feature of their cosmic situation. Yet even here, there is a kind of hope. If a void civilization developed, they would prove that life can arise and flourish even in the most isolated circumstances. Their very existence would be a testament to life's tenacity, its ability to find footholds in unlikely places, and if they were to somehow become aware of the broader cosmic web beyond their void, they would know that they are not fundamentally alone in the universe, even if they are practically alone in their own cosmic neighborhood. The same fundamental physics, the same chemistry of life, the same possibilities for mind and meaning extend throughout the cosmos, linking them to the universal story even in their isolation. I have been speaking of the Boötes Void as though it were unique, and in many ways it is, being the largest known void of its kind, but it is important to understand that it is not alone. Our universe contains countless voids of various sizes, and the study of these voids as a population is an active area of cosmological research. The local void, which our own Milky Way sits near the edge of, is one of the closest and best studied. Discovered in the 1980s, it stretches about 150 million light-years across, and likely has influenced our own galaxy's motion through space. The Milky Way, along with our local group of galaxies, appears to be moving away from the local void at about 250 kilometers per second, pushed by the differential gravitational pull of matter concentrations on the other side of us. This is a reminder that voids are not passive features of the cosmic landscape, but active participants in the dynamics of structure formation. The Sculptor Void, located about 400 million light-years away in the direction of the Sculptor constellation, is another notable example. The Eridanus supervoid, potentially associated with the CMB cold spot, spans about 1 billion light-years and is one of the largest known structures in the universe. The Giant Void, sometimes called the Giant Void in the Microscopium Sculptor Pisces Volans region, is another candidate for extreme void status. Each of these voids contributes to our understanding of cosmic structure and evolution. Together, they paint a picture of a universe that is fundamentally lumpy, organized into a web of filaments and clusters with vast empty regions between them. This lumpiness is crucial for our existence. If matter were distributed uniformly, there would be no galaxies, no stars, no planets, no life. The voids, nearest by concentrating matter elsewhere, enable the complexity that we depend on. At the same time, the voids represent a kind of limit or boundary to the habitable universe. The matter within voids is too diffuse to form significant structures. Dark matter halos are sparse and small. Gas cannot cool and collapse to form stars. The billions of light years within large voids are essentially sterile, at least in terms of the kind of material complexity that could support life. When we map the cosmic web and identify the voids, we're also mapping the habitable zones of the universe, the regions where stars and planets and potentially life can exist. I want to return now to the scientific frontiers, to what we hope to learn in the coming years and decades about the Boötes Void and cosmic voids more generally. One major goal is to refine our measurements of the Boötes Void's properties. Despite decades of study, there is still significant uncertainty about its exact size, shape, and internal density. Some estimates place its diameter at 330 million light-years, others suggest it might be closer to 500 million. More complete galaxy surveys and improved redshift measurements will help constrain these values. We also want to better understand the void's internal structure, including that mysterious tubular distribution of galaxies I mentioned earlier. Higher resolution maps might reveal whether this structure is a genuine feature or an artifact of incomplete sampling. Another frontier is using voids to constrain cosmological parameters. The abundance of voids, their size distribution, and their shapes are all sensitive to the properties of dark matter and dark energy. If dark matter is cold, as the standard model assumes, we expect voids with certain characteristics. If dark matter is warm or has unusual properties, void characteristics would differ. Similarly, different models of dark energy predict different void evolution. As our surveys become more complete, and our statistical methods more sophisticated, voids will become increasingly powerful probes of fundamental physics. The connection between voids and the CMB remains an active research area. The integrated Sachs-Wolf effect, which I described earlier, provides a way to detect voids using CMB data, even when galaxy surveys are incomplete. Upcoming CMB experiments with improved sensitivity and resolution will enable more precise ISW measurements. If there are other cold spot-like anomalies in the CMB associated with previously unknown supervoids, we might be able to detect them. Conversely, detailed ISW studies might reveal that some apparent voids are not as empty as galaxy surveys suggest, if they produce stronger ISW signals than expected. There is also the tantalizing possibility that the study of cosmic voids might provide evidence for physics beyond the standard model. If voids grow faster than expected, it might indicate that dark energy is not constant but varies over time, a scenario called quintessence. If void shapes are distorted in unexpected ways, it might indicate modifications to general relativity on large scales. If the distribution of voids shows anomalous features, it might be a clue about the topology or global structure of the universe. None of these discoveries is guaranteed, but the possibility that voids hold keys to new physics keeps researchers engaged. I am also intrigued by the potential for citizen science contributions to void studies. Many of the galaxy surveys that enable void research, like the Sloan Digital Sky Survey and its successors, are publicly available. Amateur astronomers and interested citizens can explore these datasets, identifying galaxies and contributing to projects that classify and characterize cosmic structures. As machine learning and crowdsourcing become more powerful tools in astronomy, there will be increasing opportunities for non-professional scientists to contribute meaningfully to our understanding of cosmic voids. Let me now bring us toward a conclusion by reflecting on what the Boötes Void ultimately represents. At its most basic level, the Boötes Void is a scientific puzzle, an anomaly that challenges our understanding of cosmic structure formation. Its existence pushed cosmologists to examine their models more carefully, to consider whether additional physics might be required, and to undertake detailed observational campaigns to characterize its properties. In this sense, it exemplifies how science progresses through the confrontation between theory and unexpected observations. But the Boötes Void is also something more than a scientific puzzle. It is an invitation to contemplate the nature of existence itself. The vast emptiness of the void, the near total absence of matter and structure across hundreds of millions of light-years, confronts us with a universe far stranger and more varied than our everyday experience suggests. We're used to a world full of things, matter arranged in countless forms from atoms to galaxies. The void reminds us that nothingness is equally fundamental to the universe's character, that absence and presence are partners in the cosmic dance. When I think about the Boötes Void, I feel a complex mixture of emotions. There is awe at its scale, at the sheer audacity of nature in creating something so immense and so empty. There is curiosity about its origin, about what cosmic processes could have evacuated such a vast region. There is a kind of existential vertigo at contemplating the isolation that a void civilization would experience. And there is gratitude that we live in a rich, dense region of the cosmos where galaxies cluster and interact, where the night sky is full of wonders, where we have countless cosmic neighbors even if we have not yet found evidence of life among them. The Boötes Void stands as a monument to the universe's capacity to surprise us. For all our scientific progress, for all the equations and simulations and observations that have brought us so far in understanding the cosmos, there are still phenomena that make us pause and wonder. The universe is not fully tamed, not fully explained. Mystery remains, and with it the excitement of discovery. As we come to the end of this journey, I want to leave you with a final image. Tonight, if your skies are clear and the season is right, you might be able to look up and find the constellation Boötes. It is not one of the most famous constellations, lacking the dramatic shapes of Orion or the romantic associations of the zodiacal figures. But somewhere in that direction, 700 million light-years away, lies the largest void we have ever found. A region where 300 million light-years of space contain almost nothing at all. When you look that way, you're looking at the universe's greatest mystery of emptiness. You're looking at a place that should not exist according to our best theories. You're looking at a cosmic anomaly that has inspired decades of scientific investigation and philosophical reflection. And you're looking at a reminder of how much we still have to learn, how much still surprises us, how much the universe exceeds our imagination. The Boötes Void is not just an absence, it is a presence, a feature of our cosmos as significant in its way as the grandest galaxy cluster. It has shaped the matter around it, influenced the cosmic web's evolution, and challenged human minds to expand their understanding. In studying it, we study the universe's deepest structure. In contemplating it, we contemplate our own place in a cosmos of staggering scale and variety. I hope this exploration has given you a new appreciation for the void, for emptiness as a cosmic phenomenon, and for the ongoing adventure of cosmological discovery. The questions remain open, the mystery persists, and the void waits, patient and vast and almost entirely empty, for us to unlock its secrets. If you have stayed with me through this journey to the edge of nothingness and back, thank you. Your curiosity and your willingness to contemplate these cosmic mysteries make the work of science communication worthwhile. If you have not already, please consider subscribing to this channel for more explorations of the universe's strangest phenomena. Leave a comment sharing your thoughts on the Boötes Void, because I am genuinely curious what questions and reflections this journey has sparked in you, and share this video with someone who looks up at the stars and wonders what else is out there, even if the answer sometimes is almost nothing. The universe is vast beyond comprehension. The Boötes Void shows us that some of that vastness is empty beyond comprehension. But the fact that we can know this, that we can measure and map and theorize about a void hundreds of millions of light-years across, shows that the human mind too is capable of traversing great distances. We may be small and brief in cosmic terms, but our understanding reaches far, and our wonder reaches farther still. Look up tonight, look toward Boötes, and know that you are seeing the direction of the largest known void in the universe, a place so empty that it challenges our understanding of reality itself. That knowledge is yours now, that wonder is yours, and the mystery, the beautiful unsolved mystery of why such a void exists, that is yours too, to contemplate and explore and perhaps someday help to solve. The Boötes Void is out there, waiting. What will we discover next about this impossible emptiness? Only time and continued investigation will tell. But one thing is certain, the universe still has secrets to share, and the joy of discovery is far from exhausted. In the vast darkness of the cosmic void, the light of human curiosity still shines. We began this journey with a question. What if I told you there is a place in our universe so impossibly empty that it should not exist? Now you know the answer. The place is real. The void is there. And the question of why it exists, why 330 million light-years can contain almost nothing, remains one of the deepest mysteries in cosmology. It is a mystery worthy of our attention, our research, and our wonder. So the next time someone asks you what the largest structure in the universe is, you can tell them it might not be a structure at all. It might be an absence, a void, a vast cosmic nothing that somehow is one of the most significant somethings we have ever discovered. The Boötes Void is the universe's way of reminding us that what is not there can be just as important as what is. And in that reminder lies a profound truth about existence itself, a truth that scientists and philosophers will continue exploring for generations to come. This is the void so large it should not exist, and yet it does, and in its impossible existence lies endless wonder. Keep looking up, keep asking questions, and never stop wondering about what else the universe might be hiding in plain sight, whether in the brilliance of a billion galaxies or in the darkness of the emptiest void. From this small world on the edge of our own modest galactic void, we have reached out with our minds to touch a mystery 330 million light-years across. That is no small achievement for a species that has existed for the blink of a cosmic eye. Whatever the Boötes Void ultimately turns out to be, however its mystery is eventually resolved, the fact that we are here asking the questions is itself a kind of answer to the universe's emptiness. Where there is curiosity, there is light. Where there is wonder, there is meaning. And where there are minds reaching toward the stars, even the vastest void is not entirely empty. This has been our journey into the void so large it should not exist. Thank you for taking it with me. The universe awaits our next exploration. Until then, may your skies be clear, your questions be bold, and your wonder be boundless. The void remembers nothing, but we will remember the void, and in remembering, give meaning to even the deepest cosmic darkness. 330 million light-years of almost nothing, and somehow it might be telling us everything. Succès. From the edge of existence to the heart of emptiness, the Boötes Void stands as the universe's greatest monument to mystery. We have travelled together through its history, its science, its implications, and its wonder. What began as a gap in astronomers' data has become one of the most profound questions in cosmology. What started as an apparent error has revealed a truth about our universe that we are still struggling to understand. The void awaits, the mystery continues, and the human journey of cosmic discovery goes on. In the blackness between the stars, in the silence between the galaxies, in the emptiness that stretches beyond imagination, there is a story being told. It is a story of gravity and time, of matter and its absence, of the forces that shaped our universe from its earliest moments to its unimaginable future. The Boötes Void is a chapter in that story, and we are privileged to be the readers who have begun to decipher its meaning. What will the next generation of astronomers discover about this impossible void? What new theories will emerge to explain its existence? What revelations await us as our telescopes grow more powerful and our understanding deepens? These questions animate the scientific enterprise. They keep researchers working through the night, processing data, testing hypotheses, reaching toward answers that might reshape our understanding of everything. And even if we never fully solve the mystery of the Boötes Void, even if some aspects of its existence forever elude our understanding, the journey itself will have been worthwhile, for in the pursuit of understanding we become more than we were. In the contemplation of cosmic mysteries, we expand the boundaries of the known and touch the hem of the infinite. The void may be empty of matter, but our engagement with it fills the universe with meaning. So here we are, at the end of our expedition, having travelled hundreds of millions of light-years in imagination to visit the largest known void in existence. We have seen how it was discovered, explored the theories of its formation, contemplated what life within it might be like, and reflected on its implications for the fate of all cosmic structure. We have touched on questions of science and philosophy, physics and meaning, evidence and wonder. The Boötes Void has been our guide into some of the deepest questions humans have ever asked, and now it is time to return home, back to our small planet orbiting its ordinary star in its relatively dense galactic neighbourhood. But we return changed, with new knowledge and new perspectives. We return knowing that the universe is even stranger than we imagined, that emptiness on cosmic scales is just as remarkable as the most crowded galaxy cluster, that there is still so much we do not understand. The Boötes Void will still be there tomorrow, and the day after, and for billions of years to come. It will continue to expand as dark energy stretches the cosmic web. It will continue to challenge our theories as we gather more data. It will continue to inspire wonder in anyone who learns of its existence, and perhaps, someday, it will finally yield its secrets to human understanding. Until then, it remains what it has always been, the void so large it should not exist. A cosmic mystery written in darkness, a challenge and an invitation, a monument to how much we have learned and how much we have yet to discover. The universe is vast and most of it is empty. But in that emptiness, there is structure. In that nothingness, there is meaning. And in the human mind contemplating the void, there is something the universe has never had before, a consciousness that can ask why. Why is there a void so large it should not exist? We do not fully know, but we are asking, and in the asking, the void becomes a bridge between what we know and what we may someday understand. This is the story of the Boötes Void. This is the story of cosmic emptiness. This is the story of human minds reaching across unimaginable distances to touch the face of mystery, and this is only the beginning. Thank you for joining me on this journey into the void. The adventure continues, and I hope you will be there for what comes next. The universe has many more secrets to share, and together we will explore them all. From the darkness of the Boötes Void to wherever our next journey takes us, keep wondering, keep questioning, keep looking up. The cosmos awaits. End.